Now, let us move on to the next important topic of group delay, which is very closely tied to the phase response. So, we will define what group delay is. So, this is the notation that is used for group delay, and this is nothing but the negative derivative of phi of omega, where phi of omega is the continuous phase function. So, this is the unwrapped phase, and for systems with rational transfer function, you can always write the frequency response as amplitude response times e to the j continuous phase response. So, that is always possible, and hence for the class of systems that we are interested in, phi of omega being a continuous phase function is the actual behavior, and the group delay is the negative derivative of phi of omega. And since in general phi of omega is non-linear, tau g of omega is also non-linear, except when phi of omega is piecewise linear, and we have seen that phi of omega can be piecewise linear when you have zeros on the unit circle, right. We have seen specific examples where you can have linear phase, and the examples that we have seen so far is zeros on the unit circle. So, when phi of omega is piecewise linear, then tau g of omega is constant. The only question that might come up in your mind is, for example, for the cases that we have seen earlier, the phase response is something like this. And you have this jump, and this jump is of value pi, and note that phase unwrapping cannot get rid of jumps of pi in the magnitude times e to the j phase angle response. However, if you write this as amplitude times e to the j phase, you will get rid of these jumps of pi, because this jump of pi will get absorbed in the amplitude, therefore, there are no issues. But even in this representation, if you differentiate this, this will give you a constant group delay, but at this point at omega equal to 0, you will have an impulse because of this discontinuity, and this might cause some worry, saying, well, there is an impulsive component to the derivative, but note that at this frequency value at omega equal to 0, because the 0 is on the unit circle, the magnitude response goes to 0. Therefore, there is no component in the output at this frequency, and hence this impulse appearing is not an issue. And if you look at this from the other representations point of view, namely amplitude times e to the j phase angle, that phase angle does not contain any jumps. Therefore, whichever representation you look at, there are no issues in terms of the group delay. And in general, tau g of omega can take on any value including non-integer values. And the reason why I am mentioning this is we are going to give a physical meaning to group delay, and this delay need not necessarily be an integer. Therefore, group delay can take on fractional values, but this should not cause us any problems because we know what it means to import fractional delay to sequences. And for systems with real valued impulse response, for each of n that is real valued, phi of omega is odd symmetric. This implies that tau g of omega, which is its derivative, will be, what will be the symmetry of tau g of omega? Will be even symmetric. Again, this is satisfying because you expect the delay to be the same for plus omega and minus omega naught. For plus omega naught and minus omega naught, which corresponds to a component at omega naught, you want the delay to be the same for real valued signal. So, everything is falling in place. So, this is satisfying, which is what you would expect for systems with real valued impulse response. You do not want plus omega naught and minus omega naught suffering different delays for a real valued system, and that falls out from the symmetry property of phase angle and its corresponding derivative. The other thing that we have seen is if there is a 0 or pole close to the unit circle, then the phase response, when you go around the unit circle, when you cross a pole or a 0 that is near, the phase response will change very rapidly. Therefore, we have seen this kind of phase response, right. The 0 or pole being very close will cause a very rapid change, and the corresponding group delay will have a spike, because that after all is the derivative of the group delay. All right. Actually, this is minus tau. The way I have drawn, this is minus tau g of omega. Anyway, it will have a spike near or a pole or a 0, because the phase change is rapid. You will have a very rapid increase in the group delay. Now, let us try to get a feel for what this group delay does in practice. So, let us look at a practical example. I have an input which is this, and this is 300 samples long, but beyond this point it is all zeros. In the beginning it has 3 pulses. The envelope of these 3 pulses is the same, and inside it has oscillations. So, the first pulse has the lowest oscillation, the second pulse has an intermediate frequency of oscillation, and the third pulse has the highest frequency of oscillation. So, this is the input. Now, what I am going to do is I am going to pass this through a system. and I want to observe the output behavior. The system I am going to pass through has actually two parts. So, this is H1 of Z. The second system is H2 of Z. H2 of Z happens to be all pass. So, it cannot change the overall magnitude response, and this has a certain frequency response based on its poles and zeros. Okay. Now, let us look at what the first system is. Let us look at what H1 of Z is. So, this is what the first system is, and you can expect gain around this frequency region to be high, because you are getting close to this pole. This 0 is almost on the unit circle, therefore, you can expect a frequency response dip here, all right. And sure enough, if you plot the frequency response of this system, so this is what the frequency response is. Pole 0 plot and the corresponding frequency response. So, around this region there is a peak, and around this region there is a dip. So, this is the overall frequency response corresponding to this pole 0 plot, and this is the phase response. And notice that in this region the phase response changes more rapidly compared to elsewhere because of this pole, and similarly in this region the phase response changes even more rapidly because this is very close to the unit circle. So, closer to the root is to the unit circle, more rapid will be the phase response change. So, this change in phase response is due to this pole, this change in phase response is due to this 0, all right. So, this is the system and its frequency response, pole 0 plot and its frequency response. Now, the second system is all pass. So, now let me plot the pole 0 plot of the all pass system. So, this is the pole 0 plot, and this is indeed all pass. So, I have a set of 4 poles that are very close to the unit circle, equally spaced, and you see the number 2 here, it means it is a second order 0. Actually all of them are double poles, all of them are double zeros. Because of numerical precision in MATLAB, not all of them are being marked as second order zeros and second order poles. Okay. Ideally they are second order, all of them are second order poles and second order 0, therefore, you should have the label 2 for each and every root, okay. And this is all pass. Now, you can look at the frequency response. So, frequency response, there should be no surprises here. So, this is freq Z of B comma A. So, this is the corresponding frequency response. This magnitude, if you notice, this is 10 to the minus 3. So, that is why you see something here, and really if you zoom out, this fluctuation will not be seen. You are seeing this fluctuation as if it is something significant because the scale is very, very narrow. It is zoomed in. If I zoom out, this will be a constant, and this change of 10 to the minus 3 will hardly be visible. And again, this is happening because the poles are not exactly at the location they have to be because of numerical precision. So, this is the all pass section, its magnitude is all 1, and this is the phase response, and the phase response is changing very, very rapidly. This is where the 4 poles and 4 zeros are. All the 4 poles are very close to the unit circle. The zeros are at the corresponding reflected position. Because the pole is close to the unit circle, the reflected 0 also is at the very close location to the unit circle. And because of that, this phase response is changing extremely rapidly. And this is the constant magnitude response. Ideally, this should be 1. You see this because of some numerical errors. If you zoom out, this will be 1. And this is the phase response. Now, if we cascade both these systems together, suppose I cascade them together. I have to cascade the earlier system shown with the all pass. The vectors B1 and A1 have that. And if you recall, this was the frequency response that was shown earlier. This remains unchanged because it is in cascade with the all pass system. So, this is exactly what it was earlier, but what is significantly different is this is the phase response of the overall system, which is the sum of the phase response of the simple system that was shown earlier with 2 poles and 2 zeros cascaded with the all pass system that we just saw, and it is dominated by this rapid change in phase over a small change in frequency value. And if you look at the corresponding pole 0 plot, so this is what the corresponding pole 0 plot is. So, this is exactly the all pass section that was there earlier, and this is the H1 of Z frequency response. And now what we are going to do is, we are going to take the input that I had shown earlier with 3 pulses with 3 different carrier frequencies, and then we are going to pass it through this system, and then we are going to see what the output is going to be. Let me So, this is what I had shown earlier, the input. Now, I am going to form the output Y. I am going to filter it. The system is B1 A1, which is the overall system, which is the cascade of H1 and H2, and the input is X. So, this is what the output Y is going to be after filtering it through this system whose pole 0 plot is shown here, and the input X is what is shown in the first subplot. Now, let me plot Y, and I am going to plot it below the first. All right. So, this is what the output is. Now, let us get a feel for what is going on. Remember, there was a dip in the frequency response due to the 0. All right. If you recall, there was a 0 very close to the unit circle, and the frequency response had a valley. And this pulse, which had the highest frequency of oscillation, it so happens that the frequency response sharp null at that frequency, and hence this gets killed, no issues, alright. So, this gets killed, which is why you do not see that happening here. What is the other striking thing that you see when you look at the, so this is gone, but among the two pulses that are remaining, what is it that you see? The first pulse and the second pulse, the order has been reversed, right. The first pulse and the second pulse, the order has been reversed. First pulse occurred earlier in time compared to the second pulse. At the output, it is occurring later, and this is exactly because of group delay. Now, if you look at this, this starts at time index of 0. Now, if you look at this, roughly this starts at time index of 150. So, this has suffered a delay of 150 samples. Okay. Now, let us again use MATLAB's help, and then plot group delay. As I said, MATLAB can do anything you want short of those two items, eating your lunch and writing your quizzes. So, now let us plot group delay B1 A1, all right. So, this is the group delay here, and remember the all pass section had a set of 4 poles and zeros at a certain location which corresponds to a certain frequency region, and at that frequency region you had the greatest change in phase response. You can expect the group delay to have a spike around that region, and it so happens that it is exactly at 0.2 in MATLAB's notation, or it is actually 0.1 in the conventional notation, and the delay that you see here is 150 samples. So, this 150 is no accident. This 150 samples is exactly the delay that the first pulse underwent and occurred 150 samples later. It so happens that the first pulse frequency location is such that it is around that area of frequency. Its frequency content is exactly where you have the sharpest change in phase, and therefore, the largest group delay, and this group delay is manifesting itself as that component appearing 150 samples later at the output. So, this is why it is called group delay, all right, and hence you see in this example dramatically the order of the two pulses gets reversed. First pulse and second pulse switch order, and if you look at this, the second pulse is practically unchanged. There is a very slight delay, and the reason is at this particular frequency the group delay is not much at all. Yeah, question? Yes. So, if you, that is a very good observation you have made. This is exactly where the 0 is going to be. Therefore, there is not going to be any frequency component here. So, the point related to that question is very important, what he raised. If group delay physically means delaying of the signal by so many samples, then does it mean if the group delay is negative, the system can advance your input, which means this is non-causal, which is not possible. But the important point to note is, for all practical filters in the passband, the group delay will always be positive, and if they go negative, it will be in the stop band, which really does not matter, there is no physical interpretation.